Okay, so this is the Casio fx-991CW. It's a nice little calculator, costs about 20 bucks right now, and it operates off of a solar cell, which is one of the reasons I picked it up. I wanted to get a calculator that I can use when I go out. That's very cheap and simple, and also has some scientific functionality. So you can see it has a lot of stuff here. Calculate statistics, distribution, spreadsheet, table, equation, inequalities, complex, base n, matrix and vector, mathematics, ratio, and a couple of random distribution things here for coins and dice. So this calculator does have long-term storage, but for the variables specifically, so you can store 9 numbers long term. And I think that they're stored, there is a battery that goes into this, not to make it operate. I mean, it'll help it operate for when the solar panel goes out. You can see up there in the top right corner when it's operating off of solar. And it's actually a pretty good sensor. Like if I really block this guy, just a little bit of light goes in. This is light just from this room. It still works pretty good. So this is, I think it will hardly ever work off that battery. So I think that battery is there for the long-term storage of these variables. But you can't store anything else. So, for example, if I want to go to the spreadsheet here and I was to do 1, 2, 3, put some data in there. If I press this on button, you'll see that it clears out. If I do 1, 2, 3, and then I turn off the calculator and then turn it back on, you'll see the data's gone. Now the data will remain if I say go to the home and come up here to do a calculation, 5 plus 3, and then go back home, back down to the spreadsheet. We'll still have our data in there. And the spreadsheet isn't huge. It goes to 45 rows, 5 columns. Now you might say, oh, there's lots of really nice calculators out there. There's even in the Casio line, there's calculators that can store data. I do have a Texas Instruments TI Inspire CXCAS. So I do have this one. The problem is carrying around a calculator that has an MSRP of $150 is not something I'm keen on. I even have it in this case. I have this big old case for it just to carry it around because it's a nice calculator, and I'm kind of particular about my things getting scratched and gross. So carrying that bag around and carrying around an expensive calculator, it kind of sucks. But a $20 calculator that is very light, because there's no battery outside of the little, there's a little coin battery in here. So it's very light to carry. I can put it in my pocket, take it wherever I want, and do calculations out when I'm, eating with family or whatever. So that's why I like this calculator a lot, just because I don't ever have to worry about charging it. I can keep it in my pocket forever, and I know I can just whip it out and use it whenever. And I'm not afraid of this one getting a little scuffed. I might even buy a second one as a backup to keep in storage for later, even though the solar cell may go bad. Either way. Yeah, so the question here is, how do we extract data from this calculator? Like a spreadsheet is cool, even if it is small. Typically you do calculations not to just get a result that you plug into a function somewhere else, but to maybe store it for later, to reanalyze it, maybe in another tool, something like that. Like you're out and you have an idea over dinner and you type out a little spreadsheet of some equations, and then you want to do something more with it. Well, this calculator has a built-in QR code, so you can export the current screen of data, not just the screen, the current set of data. Like if I'm in the spreadsheet, it'll export the whole spreadsheet. You'll see it says 1 of 1 over here. So when it gets, the data is too large, like if you fill the whole spreadsheet, you'll get multiples, like 3, 4, whatever, QR codes that you scan. And then you have to concatenate the strings together and put them on to the website. So one of the issues is that it uses Casio's proprietary website, which may be down in, who knows, even yet next year or 10 years from now. And then this feature becomes obsolete. So I wanted a way of being able to acquire this information on my computer and be able to visualize it, or make a Android app or whatever, so that I can scan 1, 2, 3, 4 and not have to manually concatenate the QR data, just have it automatically do it. And then have that data that I could just copy and paste it or export to a CSV or whatever. So that is my primary issue, is I don't want to rely on their website and their web service for that. Who knows if they'll paywall the web service or anything like that as well. So you can also export regular calculations, like if I did a 5 squared here and then export it to the QR, you'll get a QR code for that, and on their website you'll see the exact thing we see here, which is the 5 squared, and then the 25 is the value, or the result. So the question then becomes, how do we do that ourselves? Well, Casio has their own built-in encoding for that QR. You'll notice inside of the QR URL there is a query string that you can extract. So we'll take a look at that and see how I've extracted this data. I actually have the program moderately working, not complete, but mostly working for the stuff I want. I can export out the Excel sheet, or the spreadsheet I should say, here, and get that data printed out to where I can copy and paste it or save it as a CSV in a command line tool. And then I have this calculate section, also mostly working with most of the functions. Some of the all the constants are in there, but a couple of functions I haven't finished completing, more the more complex, like this one here, for example, where you have this value with the fraction here, something like that. This is has a special visual encoding, which is actually different than say this one, whereas like there's a different encoding, there's different encoding keys for them. So we'll take a look at what I've done here and how I have reverse engineered it's not that hard, but reverse engineered the encoding so that I can write a program to read these QR codes and store them long term and be able to visualize them easily without the ClassWiz proprietary website for that. Also, when you export out the spreadsheet via QR to the ClassWiz website, I don't think you can export that to a CSV or anything. It's just like this visual UI with the data plugged in there that you can manipulate. So I'd like to put it in a CSV or something so I can import it into a more powerful spreadsheet program and reuse the data. Okay, so we'll take a look at this. Okay, so it's another time of day, so the lighting might have changed a little bit. But we've got some examples here of what happens when you have an equation, and then this is the QR code that is output by that equation. So we'll take a look here at just the regular equations, the equation ones first, and then we'll take a look at the ones that are related to the spreadsheet tables. So this 9 equals 9 is the main thing we're looking at here, and you can see that I've split the Q and the E off of the URL. They do just continue one after another, so this would be like E39 here, and the Q would go up here. But this whole first portion doesn't really matter. I think that this is the query string. I think that these are just device identifiers here, honestly. I think all that stuff is device identifiers. You'll notice it's the same across all of them. So I'm using the same device, the same model, everything else. So what you'll notice is that we have two things here. We have a Q and we have a E. Q I've deduced is something like quantity, perhaps, or something like that. But you'll notice that we essentially went into the calculator. I'll show you how we devised this QR. We went into the calculator and we went into the calculate mode, and I pressed 9, enter, and then got a QR from that. So that's what this first one is. So here in the first one we see we have some information here. We have a 9 here, which is one of the numbers we're looking for, and a 9 here. So let's keep that in mind, and then let's look at, say, this 3 plus 7 is 10 because it's a little more complex. We need to know, Q and E. So E, I've deduced is expression. Q is probably quantity. It's the result of the expression, or it's query. I don't know. But query doesn't make sense to me. So here we have a 3 and a 7 as part of the expression and a 10 as the result. You'll see that we have what looks to be a 10 here. And then we have, well, we have 2 3s, but this 3 is the important one. And then we have a 7 here. So now we'll look at this 3 times 9. I know that one may not have been the best selection here, but you'll see is equal to 27. Here's our 27. And here's that 3 again, and here's a 9 again. So that's how we can review this and know that E is going to be the expression and Q is going to be our answer here. But Q is very long. There's a lot of stuff going on in here. We'll take a look at the expression real quick and some information about it. So the way that the encoding works is there is some identifier and then the value that is being identified by that identifier. So you see 3 is in the beginning of all of these. Now I've cheated because I've done tons of these, but these are just some examples I pulled out. The 3 is saying that a constant number is coming next. So for example, we'll see here is 3 and the 9, and you see 9 is in our expression here. So we say a constant is coming, and there it is. And here again, we have the decimal. We'll come back to the decimal. We have 3 and a 7. So 3 is a 3, 3, 7. So you see that. And then here, down here, we have 3 to 3, 3 to 9. So it's saying a constant's coming next. Now I didn't print out one here, but let's say that we had instead of this being 3 times 9, let's imagine it was 44 times 9. So if it was something like 44 times 9, what we would have is 3, sorry, my 3 is there, 3, 4, 3, 4. And then we'd have the expression for multiply, which is right here in between, which is A8. That's our expression for multiply. You see is 3 times 9, so A8. So we'd have 3, 4, 3, 4, A8, and then the 9, so 3, 9. This would be the expression for 44 times 9. Is 3, 4, 3, 4, A8, 3, 9. So the expression you can see has an identifier and then a value or some entry to that value. And they get more complicated. We have a super complex one down here. As you can see, we have 1 plus 2 minus 3 times 4. So if we look, there's 3, 1, A26. So we can even just write this out here. So 3, 1 is going to be the value 1. A6 is going to be plus. 3, 2 is going to be 2. A7 is going to be minus. 3, 3 is going to be 3. A8 is going to be multiply. 3, 4 is going to be 4. A9 is going to be divide. And you'll notice now there is a parenthesis. So we're saying divided by these parentheses. So you'll see after that divide is a 6, 0, which is going to be the left parenthesis. And then we have a 3, 5, so that's going to be 5. And then we have that 6, 0 again, so that's another parenthesis. 3, 6, so 6 is coming. Now we have D0 and D0, which are the closing ones. And then we have A6, which is plus. Now we have a new code, 7, 7, which is going to actually be sign. So I'm just going to put sign. We have 3, 1, so it's going to be the sign of 1. We have D0. Notice that D0 here is that closing parenthesis. So this encoding is pretty straightforward. It's nothing much more than matching the encoding to the direct character. They don't do any kind of tricky stuff. There is some stuff later on that is not a part of the sheet that shows how to work with things that have different arguments. So some of these functions can have multiple arguments. And I think the code for that is you would have like an A1, which says there's an argument coming. So it'd be like A1, some number. So it'd be like A1, 3, 5 to put in 5. And then A1 again for the next argument. And then when the entire function or expression there is done, it ends with B1. Or maybe it's 1A and 1B. That's probably what it is, 1A, 1B. So this encoding is just very straightforward. This just prints straight into characters and numbers. So the code for this becomes pretty simple. Now the question is about that Q value. So that Q value you see has, like here we have this value is 2.88277, so on and so forth. You see that 2.88277, so on and so forth. Notice there's no encoding here for a decimal. It just is all the numbers laid out. And we'll get to that in a second. So let's look at 9. We can say 9 is inside a Q right there, and we'll notice that right here is a few characters. We have 1, 0, 0. We're going to ignore the right-hand side for now, and probably for the entirety of this video. It's not exactly needed as far as I can tell yet. So let's look at this one, 10. Notice we have 10, but notice that here it's 101. 101 right there. So the reasoning for this is you can think of the 1 as a terminator saying this is the end of where our numbers are going. So let's just, we can even put a line to say no more numbers are allowed after this. So this space here is the total space for our result. So it does have a limit, obviously. I think this is about 23 or 24 characters is the limit here. And then what I want to focus on is this 0, 0 and this 0, 1. Because what this is the decimal place. So 0, 0 means the decimal place is after the 9. You can think of this as you take this pairing, 0, 0, and then you just plus 1. You just think of it like that. So we go to where the 9 is, we add 1, and the decimal is going to go after the 9. Obviously, it's all zeros there, so we don't need it. We can get rid of it. So the result is just 9. So let's take a look at here. We have 0, 1, so it would be 0, 1 plus 1, and that'll give us 1, 0, and then the decimal would go after that. And of course, all those would be trimmed off because it's a 0 in the decimal places there. So same thing with this 2, 7 here. We have the 0, 1, so 0, 1 plus 1 is going to be our result here. So it's 2 again, so we start at the front, 1, 2, put a decimal there. Now we can look at this 0.0009 and make and throw a wrench in here when it comes to 0 dot something. So notice we have our 0, 9, and then a bunch of 0, 0. So, and you'll also notice that we don't have the 1 here anymore. This is still the place where we break, but it turned from a 1 to a 0 because of this 0 here. So what's happening here? Because obviously there's only 1 9 there, and it's right at the beginning, so how do we capture that there's in fact 3 zeros before that 9 right there? And the way that we capture it, actually this one on the right, because the left one is the expression, so these 3 zeros. So you notice there's a 96 here. Well, this is actually counting the way that this one counts up, this one counts backwards, and whenever you count backwards from 99, you know it's going to be 0 dot and then this many zeros. So if I, for example, said, what is, let's do 99 just because it's easier to see. What is 99 minus 96? 99 being the maximum. And 99 minus 6 is going to be 3, which is those 3 zeros. Now, of course, you could I think the way that I wrote the code is 100 minus 96 is equal to 4. And that's just saying the first one is going to also be zeros because you have 4 zeros here. You just have to remember to put the decimal after the first one. So that's the entire encoding of the Q and the E. And then it's just a matter of figuring out what the different codes are, the opcodes are for the different instructions like sine and cosine and tangent and inverse tangent and so on and so forth. And also like constants like pi or Euler's number, Euler's number, I mean, and that sort of stuff. So that's the breakdown here. And we can look at this one here also because this one is not 0 dot blah, 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 blah. This is 2 dot blah, 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 blah. So what you'll notice here is if we look in our encoding here, let me see where we can line up the 1 here. Yeah. So you'll notice in this one, we have that 0, 0, right? So what do? I'm going to bring this over here. We say 0, 0 plus 1 is equal to 1, right? So we put the decimal in after 1. So here's the 2. We're always skipping that first 0. Here's the 2. We put a decimal right there. So if this was something like 28.82 in this case, then we'd have a 0, 1 here. So it would be 0, 1 plus 1 is equal to 2. And that's where we'd have 1, 2. And that's basically it. So that's just where we place the decimal is encoded there. This later half we don't even use, so don't worry about that. But this is the entire encoding for the calculation whenever you go into the setting here and go to calculate. That's the entirety of it. So we have another encoding, which is actually a lot simpler, and this one's for tables. So tables are pretty straightforward. The calculator has A through E as the table, and then some numbers. So this would be the ASCII text output we would want to see out of the console. And this is the encoding here, and I went ahead and broke it down just like in the last one. Same thing as last time. This is device identifier stuff. And then we start with a T equals T and then an SP. So we don't have the Q or the E in this. We just have T and SP. You'll notice here that we have one sequence and then we have a second sequence. And if we just look at the numbers like 1, 1, 1, 1, 2, 2, 2, 3, 3, 3, 4, 4, 4, you can see those here. 1, 1, 1, 1, 2, 2, 2, 2, 7, 7, 3, 3, 3, 3, 3, and 4, 4, 4. They're spaced, so let's, instead of going left to right, we'll go top to bottom. So we say 1, 1, 1, 5, 5, 5, 5, 1, 1, 1, 5, 5, 5, 5. Then we have our 2s, our 6s, and 7s. 2, 6, and 7. So it looks like it's in column order here. And if you'll notice, we have that same 105 at the end. Right here, 105. So you may have guessed this section is the same decimal encoding as the last one. The only thing about tables is rather than 24 numbers, we have 6. So of course, once you get into the millions, you're going to lose precision and you should probably swap to scientific notation. This number on the right will increase, so it will be 6, even though there can only be 6 here, and 0.6 plus 1 is 7, or 0.6 plus 1 is 7. Even though you don't have 7 numbers here, you can just assume that it's a 0 at the end, do a scientific notation on it. So that leaves us with this section up here. And at first, it may not make any sense, CEF80. Like, what does that have to do with these columns? But what it has to do with the columns is that this is a 4-bit number. Each one of these is 4 bits. Each one of these entries horizontally is 4 bits. So if we look at something like D, which is going to be the easiest one, you'll notice, oh, the easiest one is E. There's nothing in the E column, 0. You'll notice it's 0 there, 0 on all of it. So if we look at D, which is going to be the next easiest one, we'll see an 8. So if we had 4 bits, there, we would then, if you thought about which one would be 8, it would be as if we turned this one to 8. So it'd be 1, 0, 0, 0, right? Okay, so then what would F be in that case, right? Notice we have the F8 here. And I want to do this one because it makes it simpler and easier to view. So this would be F8. So we'll deal with just the F portion for now. So F, ignoring this, I'm just going to put a line through it to show you. F would be 1, 1, 1, 1. 1, 1, 1, 1. And then we have the 8, which is the same as our last one. So let's draw another line. We'll say 1, 0, 0, 0. So what you'll notice is this has one entry in this column here. And then the next one over has 1, 2, 3, 4, 5. It has 5 entries. So we have 5 bits here if you count. 1, 2, 3, 4, 5. So you can see that from top to bottom, because the one is over here on the left-hand side, I believe this is what you would call a little endian, where the little bit is on the end. We have 1, 2, 3, 4, and then a 5th one. So 1, 2, 3, 4, and then the 5th one. And that's what these numbers all the way over are. So you can see by counting up how many of these there are, if they were all Fs, that would be your maximum, your maximum spreadsheet column count. So now we can go to the next one here. We have an E. So you can just visually look at this and say it's 1, 1, 1, 0 for that one. And then you can visually look at this one and say it's 1, 1, 0, 0. And this one is 0, 0, 0, 0. All right? So these tell you the column behavior and which entry is filled. And this is the data, the payload. Notice it doesn't put any empty columns. This column of, or this cell here of zeros is because of this one right here. So there's no entries. So you can look at empty entries. So you can look at this as a packed. It's packed numbers. So all the numbers are packed together. And we have to use this masking system here to lay them out inside of the table format. So you just go through the mask. You say, oh, and you go from top to bottom, by the way. So you say, oh, there's one there. That's going to be the first one. I'm just going to ruin this visually. That's the first one. Then the second one. And then the third one is going to start on the next one there. A little messy. But you'll see that they just map one. Each time you see a bit, that's when you enter it. And then anytime you see a 0, you just make a blank cell. It's just all blank. And you continue all the way down and make them blank. So with that information, we can look at this next one. And it should be a lot easier to read. You can see we have the first row is blank, and then A is blank, D and E are blank. But we have something in B2, C2, B3, and C3. So if we looked at this real quick, we have 0 because obviously this is all blank here, so that's all zeros. We have zeros in the last two here, so those are all zeros. So we have 0, 0, and 0. This would be the A column of the A column, the D column, and the E. D and E. So that leaves us with these two. So of course we have 6. And if we just looked at it visually, it would be 0, 1, 1, 0, 0, 1, 1, 0. for those two. And then we can just look at the data here. We have 1, 3, 2, 4. So we would put in the 1 first, 3 second. The next one's blank, as you can see here. And this one would go here, and this one would go there. So that's how we build it out. And then you can get into, this is another visual one if it isn't making sense, but it's starting to make sense. This one's just a diagonal line, which makes it pretty clear how these are all blanks. So you see we have 8, 4, 2, 1, and notice that that's 1 bit each, and then we have an 8 on the next one. So we have 1, 0, 0, 0, 0, 1, 0, 0. I'm not even looking. I'm just assuming because I'm 0, 1 because I know the pattern. So 0, 0, 0, 1, and then the last one is 0, 0, 0, 0, 1, 0, 0, 0. And so you can see that diagonal form right there. And then you just go to the data. So 1, 2, 3, 4, 5. And that's in the diagonals. So that's the encoding for both the calculate and the tables. And those are both decoded inside of a computer program I wrote in Go, because Go is, even though C is my favorite language, Go is very fast to put things together. I really like it. So we're going to be talking first about this section here, the calculate section, and then we'll go into the table stuff. But for the calculate, I mean, technically this first section is going to be for both because we're going to be setting up the query. But yeah, we're going to need some regular expressions. So notice that we have our regular expressions here, I-U-M-S-Q-E-T. I pulled out these I-U-M-S just to have them, because why not? And then this first regular expression is just to find the QR code. And this is, some QR codes actually have Q equals and others have QR equals. I think all the examples I pulled have just Q equals. Yeah, all the examples I pulled just have Q equals, but you can have QR equals. I caught that in one of my tests, but you're just pulling out that query string with that first one. So you can think of it as query string, and then the rest is all just taking out each one of these sections. The I, the M, the S, the Q, and the E. So those are the regular expressions that we use. This is the structure. Notice it just mirrors. So we have the raw string. We have this mirroring the different query values. Then we have an answer and a decimal. And the answer is just what we're going to be pulling out of the queue. And then the decimal is just the decimal place we talked about. So it's going to be pulling out the decimal there and then the actual answer queue there based on the decimal. So those are just helpers to have to make the code easier to read when we're putting it together. So in here we just pass in a URL. We find all matches off of that initial regular expression, which is to just find the query string. We check for errors, we return it. Otherwise, we're going to grab, this is very hard-coded, but it doesn't really matter. The calculator, it doesn't update. There's no USB ports or anything. It is what it is. So we are pretty safe with leaving it at that, with some hard-coded values in here. And then you can see I just have, I set the raw query, and then I pull all of those segments. And then we call this clean function, which just goes through and cleans up, like gets rid of the, for example, when we pull these, we don't want the U minus there or the pluses or any of that other stuff. We don't really care about that. We just want the value here. So, well, we do want the pluses, and those are captured, but I mean the minuses, so like U minus and M minus and E minus. We don't need those. So that gets cleaned up. And also inside of the this clean function, it sets the answer in the decimal. So the pulling of the segment is pretty straightforward. You just same regular expression, return blanks on any errors, and then the same kind of hard-coded values. where we trim. The first match is going to be the like Q minus, and then we're going to trim that off the beginning of, or trim that off the end of the last query, because notice these queries end with looking ahead for either a match of a letter with a minus sign or the end of the string. So we're just trimming off this letter and the minus sign if one exists. So that's it for the query. We use this to just parse the entire structure, which we'll then reuse. So let's actually look at this next one here. So here is the read number function. So if you recall, we have to pull a number in two different places. So here we need to pull this number, this 27 or this 2.8, blah blah blah, with this decimal place. And then inside of the table, we need to do the same thing here. We need to pull this number with that decimal place. So those two overlap, and since they share it, we have one function here to deal with pulling out a number with that encoding. We have the decimal code here, which is going to be that 01 or whatever it is at the end. So when we look here, we're talking about, let's look at one that isn't 00. We're looking at like this 96 or this 01. That's what's going to be coming in as the decimal code, and then the sequence is everything before that, not including the 1 at the end. So that would be, for example, since there's less numbers on this sheet, that would be, for example, like this sequence of 4s here before the 1. And on this sheet, now that I've said that, is going to be this 9 and all these zeros here. Okay, so that's basically what we do, and then with those two pieces of information, we can extract it all out. So we don't want a 01. We don't want the 0 in the leading space at all, so we remove it here. We convert that to a number, and then we add 1 to it. If you remember, we have to add 1 to it from what we discussed in the previous pages. So if I just have a hard-coded, if the decimal is 50 here, even though I only need 24 when it wraps around. So remember, we have this case, we have the case here where we have this number 96. So I just took the safe route and I just said, if it's greater than 50, then it's going to be a decimal, 0 dot something. Otherwise, it's going to be not. So this is 0 dot 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 dot. I guess dots don't make sense. X dot 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 dot. Okay. So in this case, we just create a string builder. We're going to write our 0 dot at the beginning, and then we're going to go through 100 minus the length of the sequence here, and we're going to find out how many zeros we need to place after that decimal, because it could be like 0.000006 or something like that, right? Or it could also be 0.1234. So this is just figuring out how many leading zeros we need. Then we have just a very simple, this block just goes through and writes each one of the numbers. So if that Q was 0.0217, 0.0217, then it's going to be writing this 217 that it got from the sequence here. So that's basically it for decimals. And then when we look at the whole number here, or sorry, moving some papers. We look at this, the number before the decimal. We're looking for, we want to go through the sequence, and then we want to figure out all the zeros at the end. So if you remember, we have this case where we have, for example, something like here, this one. We have something like 27 and then a bunch of zeros. We just wanted to delete all these zeros. That's essentially all that's happening here. So this will be set up to delete all of those zeros because this end is being pulled up towards that. So remove zeros. And then we have the placing of the decimal. So if the decimal is greater than the sequence, and this is in the case of the table. So if we had 1,000,000, for example, here, if you'll notice we have 11111 here. So if we had 1,000,000, because there's only 6 slots, it would be 100,000. That would be the 100,000. We'd have that 1 at the end, and then we'd have 06 instead of, I'm off the train. And we have 06 instead of 05. And this is telling us that there is 1, 2, 3, 4, 5, 6 of those, and plus an extra 0 at the end. So that's what we're looking at in this section right here, is the case where we need to add extra zeros. And then we have our last case, which is we're actually going to place a decimal. So we're going to essentially find the location and then write the decimal in the string. And then we're returning all that. So that's the different sections of parsing out that Q number, which is probably the longest function in the program. And that's basically the rest is pretty straightforward. So if we look at the decoder, when we go into the decoder code, it's pretty straightforward here. We're going to have multiple encodings, so think of like the A6 or the A7 that we saw for like plus and minus, and think of the like 3 saying that a constant number is coming next. That's what these encodings are. The decoder is just a list of encodings, as you can see actually here. And then we have a function, just a helper function to add an encoding, which just pushes the encoding in. You'll notice that we do a slices sort func, where we sort the encodings by the longest encoding first. So for example, A6 and A7 should be before 3. So even if I added 3 first, it's going to wind up at the end because it's shorter. And that's just because, you know, what if we had a code that was 36 or something, and that was like one of the codes we had. If we had that after, then we'd have an issue where 3 would always be executed and this would never happen. So we want to sort by the longest ones first in this case. That's all that is. And then we have a very simple decode. We say if we are using a spreadsheet, use our spreadsheet decoder. Otherwise, use our expression decoder. So we'll start with the expression decoder because we'll do the spreadsheets last. The expression decoder is pretty optimized, where there shouldn't be any hard-coded stuff related to the decoders in here. So we create a string, we go through the query E, which is what's passed in, and then we just continue until the expression is empty. So just keep going until we have a blank expression, because we're going to be modifying this expression here to trim off the prefix of what we've read. So it's pretty much very simple logic. We essentially go through all the encodings, and then when we go through all the encodings, we check to see if it has a prefix. This is the key reason why we had to put them in length order. We're just going to go through them one by one, top to bottom as an array, and figure out which one matches the current beginning of the string. So if we had something like 3, 4, A6, 3, 5, and I think A6 is a plus, maybe A4 is a plus. I don't know. Let's just imagine A6 is a plus. We would have, this would essentially be 4 plus 5 in this case, if this was a plus. And so we want to read from the beginning. We read a 3, so it's going to go through the 3 path. Then we get a 4 because of the 3 path and how it operates. And all of the encoding stuff you can see on GitHub. We don't need to go through the different encoders. It should make sense on how these just pick and write. What, you know, some of them are direct replacements and others are, if you see a 3, read the next character and add that to the string kind of thing. So we want to see if there is a direct replacement, then we are just going to do the direct replacement. That would be the case of the A6. So A6 would be a plus, so we just write a plus sign directly in there. That's what this transform would be for A6. Otherwise, if there's a transform function, which is in the case of 3, because 3 doesn't translate to anything directly. 3 just denotes read the next number and add it to the string. So if there is a transform function, we're going to just call the function, and that function returns how many characters we read, and if there were any errors. If there was an error, we're just going to exit. Otherwise, we're going to trim off however many characters are read. So for the case of 3, 2 characters are read. The 3 is read, and the 4 is read, and the 4 is applied to the string. And notice we passed the string builder in to the transform function so that it can just write directly. Otherwise, we have an error because we either have to directly transform it or we have to have a transform function. Otherwise, we have a real problem. The read is true here is because we need to throw an error saying we went through all the encodings and we didn't find an encoder that worked with the encoding that was supplied. So we throw an error there in that case too. Otherwise, we just slap an equal sign, slap in the answer that we cleaned out and from the queue, and return that. So that's essentially how this works, and some of this may change obviously on GitHub over time, but that's the base of how we can take that information and convert it. So we're going to look at our tables now. So we need the spreadsheet. We need to know what a spreadsheet is. That's going to be important. And then we're going to need a spreadsheet decoder. Decode table. Okay. So let's start with what a spreadsheet is. So if we look here at what a spreadsheet is, it's just basically a bunch of columns and rows. We do columns and then the rows are this array of strings here. Rows. Right there. Let me get another pencil. This one is getting a little small. So we create that. So we know the column count when we create a spreadsheet. So we're just going to create that many columns. We have an insert function. You'll notice there's an extend slice here. All this does is it extends the slice. So if we passed in 3, it just ensures that there's at least 3 columns here, and if we pass 5 here, it ensures there's at least 5 rows in that column. That's all that these are. So we essentially resize if it's not large enough, and then we just directly assign the data to that cell. We have a row count function, which just counts how many rows there are based on the maximum of all of the columns. And then we have a cell, which allows us to get a value at an X and Y cell position. And then we have a string function, which is just going to go through and create a fancy printout of this spreadsheet. So we first set up our tab. This is that first tab that we see. This is actually a printout of using this function. So notice there is a blank space here, this tab before the A. So that's all that tab is. So we add that tab. Then we go through all of our columns and we print out, we have some string inside of this global variable column keys, A through Z, even though we don't need Z and we're only going to go up to E. We're essentially just going to go through and print out A through E, which is what we have here for that first column, A, B, C, D, E. And then we go into the next line and we start printing out the data. So we first we need to write the row number first. That's going to happen here. And then we just do a very simple get cell. This is that cell function that we have up here, this cell function, which we can pass in an x and y and get the string value there. That's all we're doing, is going through each cell, printing it out, adding a tab to go to the next cell to the right in that row, and then adding a new line when we finish that row, and we go to the next one, and then we return that string. So the actual spreadsheet functionality is very simple for writing that out. Then we have our decode table. So this is like the decode E that we were looking at previously, the decode expression, but this is for a table. So we ensure that it has that SP at the beginning, because notice it's always TSP. So we make sure that SP is there. Otherwise, it's an invalid. We have some invalid data, so we're going to throw an error there on that invalid data. Then we're going to trim off that SP. So this just removes SP. SP no longer there. And then we have a 12-character sequence of the columns, and that's the first section here. These are the 12-character sequence. So when we verify the table, we go through that 12-character sequence, and we make sure that we have enough data. So notice that there are 5 entries for those. So 5 entries being A, B, C, D, E. That's 5 columns. That's what it means by entries. And we want 12 times 5. So we have 5 columns times 12 characters here. So this is just another validation to make sure that the data is correct. So this is just another validation here. Validate. And then we go through and we create this table called decode column, which all this table is a bit field. It's a list of bit fields. That's the only variable. It's literally the only variable that's in there. And this bit field is an array. It's not a slice. It's an array of 12, because we know there are 12 characters in that bit field, that bit mask field. So here we go through those 12. In each one, we essentially convert it to a hexadecimal. So like CEF8, whatever. We convert that into a hexadecimal here. And then you'll notice that we're working with only 4 bits, right? When we look here, we're working with only 4 bits. So like this is F8. So there's 4 bits and then 4 bits for those 2 different separate columns. So if we're just working with those 4 bits, of course we can treat them as 1 unit byte and then do a bunch of expressions on that. But I decided to simplify it to say 4 bits. So if we're working with those 4 bits, you can imagine it's like 0, 0, 0, 0, 1, 1, 1, 1 for this first one. And for the second one, it would be 0, 0, 0, 0, 1, 0, 0, 0 kind of thing to fit into a byte, because these are 8 bits. We don't have 4-bit, the luxury of using 4 bits easily in most modern languages. So we take our bit field. We want to reverse them, because you'll notice that if we read the first one here, it's going to be a 0. So we want to reverse it. So if we reverse it, it'd be 1, 1, 1, 1, 0, 0, 0, 0 in this case. And then in this one, it would be 1, 0, 0, 0, 0, 0, 0, 0. And the reason we want to reverse it is to get essentially this stuff at the front. But we don't, when we read right to left, right? So when we read right to left, because of the little Indian nature, this is actually going to be 0 over here. And the problem is that these are flipped, because you'll notice that these here are flipped, where 8, for example, is on the far left, but 8 denotes that the first column is valid. So if we read from the end, we're going to, as the 0th index, we're going to get a 0. We actually want to get a 1. So by flipping it like this, sorry, this isn't going to be the flipped version. It's wrong. By flipping it, which is going to be 00010000. That's actually the flipped one. Sorry about that. By flipping it, we now have the one noticed on the right side instead of the left. So all I need to do is trim off these, and then when I read the 0th index, I'm going to be reading it in the correct order. So that's essentially what we're doing here. We're going to reverse it, and we're going to reverse that 8-bit value, and then we're going to shift off the 4 on the end, so we read it in the correct order. So this is just order correction. Order correction. And then we just have this here to count up how much data we're going to be reading, because remember that the data is packed. And then we're going to trim off those 12 characters and then continue through the loop, so we go through all of them. Next, we have the data count, and then times 9, because obviously last time it was reading columns. Now it's actually reading characters from left to right. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 there. So we want to make sure that we have that the data count times 9, because each data entry is going to have 9. So this is another error check. So now we actually go about the business of reading that data. Notice we use that parser read number function that we already discussed, and we're passing in the first 6 characters as the number and the last 2 as the decimal place. So yeah, nothing crazy here. Just go through and read out that number, and we're using we're reading the bit field to check here. We're reading each bit field, and if the bit is 1, then we actually do this work to parse out the number, and then we increase our which row we're on. And that's it. That's the whole program. So yeah, thank you for working through the code with me on this. Sometimes I like to look at it on paper, because it forces me to write down things in a more concise fashion, and also review it in a better way. I feel like the physical nature of it is just so much nicer. So yeah, that is the entire encoding. So now, with that all set up, we can actually go through and export out our spreadsheets and print them out as a ASCII table that we then can paste into a spreadsheet program on the desktop. So yeah, I would say mission accomplished on this one. Thanks for watching this. This has been very long, and yeah, hopefully you had fun. I had fun making it. So see you guys next time.